You know, you might think rocks are just, well, static objects. Like you pick one up, it's heavy, it sits on your desk, and it doesn't really do much.
Right.
But today, we are going to look at how they act as these highly active, meticulously detailed time capsules.
Yeah, they really are.
We're looking at a huge stack of sources today for this deep dive, and it spans this incredible range of scientific disciplines. I mean, we've got cutting-edge astrophysical research on asteroid dating, deep geological papers detailing 2.5-billion-year-old formations in the North China Craton.
Huge timescale there.
Yeah, massive. Plus analyses of Ophiolites and the Zagros suture of Iraq, and these highly technical crystallographic studies on the atomic structure of Spinel, and then finally the gemological history of a beautiful but incredibly toxic mineral.
It is, it's a massive stack of research.
Yeah.
And, the common thread running through all of it, like the guide for this entire journey is a single element on the periodic table.
Right.
Chromium.
So the mission of this deep dive is to really take you on a journey through time and space using chromium to unlock the secrets to, well, the birth of our solar system.
Exactly.
We're going to see how scientists had to literally invent a new microscopic ruler, basically, to measure the age of water in space. We'll discover how these rocks tell us when the Earth's crust first started crashing together and how a toxic saffron-colored crystal ended up painting the very first yellow caps.
It's a wild ride.
It really is. So let's just jump right in. We are dialing the clock back to the absolute dawn of the solar system, right? Like before the Earth even existed as a solid planet.
Yeah, so we are looking at a swirling, chaotic cloud of gas and dust. But even in all that chaos, chromium isotopes were already acting as like a cosmic stopwatch.
Okay.
The specific research we're looking at here is a 2015 study by Patricia Doyle and her colleagues, and it focuses on a process called aqueous alteration in chondritic asteroids.
Okay, I need to stop you there because aqueous alteration sounds like a very polite way of saying, a rock got wet.
Basically, yeah.
But we're talking about the freezing vacuum of space here. How does liquid water interact with rock in an environment where water should either instantly boil away into vapor or just freeze solid?
Right, and that is the core mechanical problem of early solar system formation. Because when the solar nebula was condensing, you had a really steep temperature gradient.
Like closer to the sun versus further away?
Exactly. Close to the early sun, it was blistering hot. Only refractory metals and silicates could condense. But further out, it was freezing.
Makes sense.
So somewhere in the middle, there was a boundary, and we call it the snow line. Beyond this line, water vapor basically skipped the liquid phase entirely and condensed directly into solid ice crystals.
Okay, so you have dust and ice floating around out there.
Right. And over millions of years, this material started to clump together or accrete, which formed planetesimals.
The ancestors of our asteroids, basically.
Yes. So you have these large bodies composed of this chaotic mixture of high-temperature silicate minerals, like olivine, intimately mixed with chunks of solid ice. But inside these early asteroids, you also had short-lived radioactive isotopes. And the critical one for our story here is aluminum-26.
Okay, wait. Where did highly radioactive aluminum come from?
Well, it was likely injected into our local nebula by a nearby supernova explosion right as our solar system was forming.
Wow, okay. Talk about good timing.
Yeah, exactly.
Yeah.
And aluminum-26 has a relatively short half-life, just about 700,000 years. So as it decayed, it released a tremendous amount of thermal energy.
So the asteroid essentially has a built-in space heater.
That's a great way to put it, yeah.
The radioactive decay of the aluminum is generating heat deep inside the rock, far away from the vacuum of space. So the pressure inside the asteroid is high enough, and the temperature gets warm enough for that trapped ice to melt into liquid water without just boiling on.
Exactly. And when that ice melts, you have hot liquid water percolating through these primitive dry silicate rocks.
Right.
The water reacts with those rocks, stripping away certain elements, depositing others, and basically precipitating entirely new secondary minerals.
And that chemical reaction is the aqueous alteration.
You got it. And one of the primary secondary minerals that form during this whole process is a type of iron-rich olivine called phaolite.
Okay, which brings us to the actual dating process, right? If this phaolite formed inside an asteroid billions of years ago and eventually pieces of that asteroid broke off, fell to Earth as meteorites.
Specifically, the ordinary and carbonaceous chondrites found in Antarctica, which is what this study looked at.
Right, so how do we look at a rock today and know the exact year it got wet in space?
Well, we rely on a different radioactive decay system for that. Manganese-53 decaying into chromium-53.
Okay,
Manganese 53 has a half-life of about 3.7 million years. When the liquid water reacted with the rock to form the Ophiolitic crystal, it locked in whatever manganese and chromium were present in the fluid at that exact moment.
Like a snapshot.
Exactly. And because we know the rate at which manganese 53 turns into chromium 53, we can measure the ratio of those isotopes in the Ophiolite today to calculate exactly when that crystal precipitated out of the water.
So chromium-53 is the stopped clock that tells us when the water flowed.
Right.
But the Doyle study caused a massive upheaval in the astrophysics community, didn't it? Because the dates they got were completely different from the accepted timeline.
They really were. The scientific consensus at the time was that this water-rock interaction happened quite a bit later in the solar system's evolution. But Doyle's team discovered that it actually happened roughly 3 million years earlier than previously believed.
Wow.
Yeah, they calculated that these specific water-rich asteroids accreted between 1.8 and 2.5 million years after the very beginning of the solar system.
Wait, but in a universe that is almost 14 billion years old, 3 million years feels like, I don't know, a rounding error. Why did a 3 million year shift rewrite the textbooks?
Because the early solar system was a highly dynamic, rapidly evolving environment. I mean, 3 million years is the difference between an asteroid forming while aluminum-26 is still highly active versus forming after the heater has completely burned out.
Oh, I see. It dictates the entire thermal history of the body.
Exactly. But more importantly, we really have to look at why the previous dates were wrong. It wasn't just a math error. It was a fundamental flaw in how the measuring equipment was calibrated.
Let's get into the machinery of this, actually, because I find this fascinating. They are using an instrument called a secondary ion mass spectrometer, or SIMS.
Yeah, a SIMS instrument. And it is incredibly complex. Basically, you place a microscopic sample of the meteorite into a high vacuum chamber.
Okay.
Then, the machine fires a focused beam of primary ions, often oxygen or cesium, right at the surface of the sample. And this beam physically bombards the crystal lattice, sputtering off atoms and molecules from the top few nanometers of the rock.
Wow.
And some of these sputtered particles become ionized, meaning they gain an electrical charge.
So you are basically using an ion laser to blast microscopic craters into the rock and vaporize it.
That's essentially it. Then, those secondary ions are accelerated by an electric field and pass through a massive electromagnet. Because a magnetic field will bend the trajectory of a moving charged particle based on its mass. The lighter isotopes bend more, and the heavier isotopes bend less.
Okay, so it sorts them.
Exactly. This separates the manganese 53 from the chromium 53 so they can hit different detectors, which allows us to count the individual atoms.
But the machine doesn't just inherently know what it's looking at, right? Like, it needs a baseline. If I buy a bathroom scale, I need to zero it out before I step on it. How do you zero out a multi-million-dollar mass spectrometer that's measuring extinct isotopes?
We'll use a standard, a piece of material with a known absolute isotopic composition.
Okay.
You measure the standard, see how the machine reads it, and use that reading to calculate what's called a relative sensitivity factor.
Got it.
Then you apply that factor to the readings you get from the unknown meteorite sample. And here is where the historical error occurred.
Oh, boy.
Previously, scientists were calibrating the SIMS using a naturally occurring magnesium-rich olivine standard, specifically one from San Carlos, Arizona.
Wait, if the Ophiolite in the meteorites is an iron-rich olivine, why were they calibrating the machine with a magnesium-rich rock? That seems like a mismatch.
Because pure natural Ophiolite is exceedingly rare on Earth. The San Carlos olivine was readily available, it was well studied, and structurally, it's similar. The assumption was just that the machine would vaporize and ionize an iron-rich olivine with the exact same efficiency as a magnesium-rich olivine.
But the physical mass and chemical bonds of iron are totally different from magnesium. I mean, when you blast it with an ion beam, an iron-heavy crystal isn't going to shatter and ionize the same way a magnesium-heavy crystal does, right?
And that is exactly what Doyle's team proved. The ionization efficiency was radically different. The relative sensitivity factor between the magnesium standard and the iron-rich meteorite sample was skewed by 60%.
60%. That's a massive margin of error on a cosmological measurement.
It's huge. To fix this, Doyle and her team, they couldn't just rely on natural Earth rocks. They had to synthesize a brand new standard in a laboratory. Yeah, they meticulously created a pure synthetic Ophiolite standard. They called it FAN 99. grown specifically to match the chemical matrix of the meteorite.
Okay.
They baked this standard, calibrated the sims with it, and only then did the true timeline of the water alteration snap into focus.
They literally had to invent a new ruler because the old one was stretching the truth.
Exactly.
So we pushed the date of liquid water back by 3 million years. We know these wet asteroids formed 1.8 to 2.5 million years after the solar system began. Why does this change our understanding of where the Earth's oceans came from?
Well, it severely challenges a very popular astrophysical framework known as the Grand Tack model.
The Grand Tack model, okay.
For a long time, there was a real problem explaining the distribution of water in the inner solar system. The assumption was that the inner solar system, where Earth, Mars, and the asteroid belt are, was simply too hot during those first few million years for water ice to condense.
So it should have been bone dry.
Right. Therefore, the asteroids in our neighborhood should have been completely dry.
If they were dry, then the water had to be delivered from somewhere else.
Exactly. The Grand Tack model proposed this violent delivery mechanism. It suggested that Jupiter, shortly after it formed, migrated inward toward the sun, plowing through the early planetary disk.
Wow.
Its massive gravity supposedly acted like a cosmic bowling ball, scattering dry material and dragging wet, icy asteroids for the deep freeze of the outer solar system inward.
Okay, so it brings the water in.
Then Jupiter supposedly tacked like a sailboat changing direction and migrated back out to its current orbit, leaving a bunch of wet asteroids in the inner solar system to eventually deliver water to Earth.
That is a very dramatic theory. I mean, Jupiter acting as a bouncer, throwing ice cubes from the back of the club all the way to the front.
It's a great visual.
But this new chromium isotope dating completely undermines that narrative, doesn't it?
It really does. Because if these phaolite crystals formed, meaning water was already melting inside these asteroids at 1.8 to 2.5 million years, we can run thermodynamic models of the solar nebula for that exact time period.
Okay.
And those models show that the snow line, that temperature threshold where water can condense into ice, was actually much closer to the sun than previously thought. It was sitting right around 2 to 4 astronomical units.
Wait, 2 to 4 astronomical units? That is exactly where the main asteroid belt sits today.
Yep. The water didn't need to be imported by Jupiter's gravitational bullying at all. The ice accreted locally. The water was a fundamental part of the local recipe from the very beginning.
That's incredible.
We had these wet, dynamically active planetesimals forming right in our planetary neighborhood, driven by the internal heat of aluminum-26, and it's all recorded by the ticking clock of chromium-53.
It's just wild how deeply interconnected everything is. A microscopic error in ionization efficiency on a mass spectrometer cascades into rewriting the orbital dynamics of Jupiter and the origin of Earth's oceans.
It's the butterfly effect, basically, but in astrophysics.
Right. Now let's fast forward a bit. The swirling dust has settled. Those early wet planetesimals and rocky bodies have smashed together, heated up, and solidified into the early Earth. We are moving from the vacuum of space to the boiling, violently active early days of our own planet.
Right, we're entering the Archean eon, which is about 2.5 billion years ago. The Earth has formed a crust, but the mantle beneath it is churning with an intensity that is, well, it's hard to even comprehend today.
So our second stack of sources brings us to the North China Craton. We are tracking chromium down into the ancient ocean floors to answer a massive geological question. When did the Earth's crust start acting like a conveyor belt? Like, when did plate tectonics actually begin?
To understand the debate here, we really have to look at the thermal mechanics of early Earth, because the planet was still retaining a massive amount of primordial heat from its accretion, and at higher concentrations of radioactive isotopes decaying in its mantle, the interior was just much hotter than it is today.
Makes sense.
So some geologists argue that this extreme heat would make the crust too soft and buoyant to to sink back down into the mantle. They proposed a stagnant lid regime where the crust was just this unbroken, squishy skin.
Right, because if the crust is too soft, you can't have rigid plates pushing against each other to build mountains or pulling apart to open oceans. It would just be a mushy, static surface.
Exactly. Conversely, other geologists argued for a mobile lid regime, suggesting that the higher heat actually drove faster convection currents in the mantle, resulting in rapid, vigorous plate tectonics.
Okay, so a fast-moving conveyor belt.
But to settle this debate, you need physical evidence. You need an ancient piece of oceanic crust that survived billions of years of geological recycling. You need an ophiolite.
What exactly is an ophiolite, and how does a piece of the ocean floor end up sitting in the middle of a continent?
Well, the ocean floor is constantly being created at mid-ocean ridges and destroyed at subduction zones, where the dense oceanic plate dives under a later continental plate.
Right, the recycling process.
Because of this constant recycling, most oceanic crust is very young. It's rarely older than 200 million years. But occasionally the mechanics of a collision go wrong,
Like a pileup.
basically. Instead of diving smoothly under the continent, a slice of the oceanic crust, along with the deep upper mantle rock attached beneath it, gets sheared off and violently thrust up onto the continental landmass. This process is called abduction.
Oh, wow. It's like a geological core sample that gets jammed onto the beach instead of sinking into the trench.
That is the perfect analogy. And that preserved cross-section is an ophiolite. Finding a complete, intact ophiolite older than 2 billion years was considered the absolute holy grail for proving Archean plate tectonics.
Which brings us to the 2002 research by Zhonghai Li, Timothy Kulikisk, and their team. They've entered into the central orogenic belt of the North China Craton.
Right.
And just to clarify, a craton is essentially the oldest, most stable, deeply rooted heart of a continental plate, right?
Yes, exactly. The North China Craton is formed by an eastern and western block that smashed together billions of years ago. And caught right in the suture zone between those two blocks, Li and his team documented the Dongguanzi ophiolite, dating it to 2.505 billion years old.
And the key to proving this wasn't just a random pile of rocks, but a true section of deep oceanic mantle was finding chromium. Specifically, they found these structures called Podiform chromitites.
Yeah, Podiform chromitites are essentially localized, highly concentrated lenses or pods of chromite rock. And they're encased within a sheath of another mantle rock called dunite. Dunite is almost entirely composed of the mineral olivine.
Okay, but why are these chromite pods so important for understanding the Archean mantle? Like, if the continents smashed together, shouldn't these rocks just be crushed into powder?
That is the brilliance of chromite. Because it crystallizes at incredibly high temperatures, often between 1200 and 1300 degrees Celsius deep within the mantle, it becomes exceptionally rigid when it cools.
Oh, I see.
So when the eastern and western blocks collided, the softer surrounding silicate rocks were sheared, folded, and completely deformed. But these dense pods of chromite acted like armored safes.
Wow.
They resisted the tectonic crushing, preserving their delicate, primary internal magmatic structures completely intact.
The structures described in the paper are just incredibly visual. They talk about nodular and orbicular textures inside the chromatite. What are we actually looking at here?
Imagine cracking open one of these pods. A nodular texture looks like thousands of perfectly spherical, dark, metallic balls of chromite sitting in a pale green matrix of dunite.
Okay.
An orbicular texture is basically the inverse. It's thin, concentric rings of chromite wrapped around rounded cores of dunite.
I'm trying to picture the physical environment that creates a rock made of perfect spheres. It sounds honestly like tapioca pearls suspended in a boiling cup of bubble tea. If the tea just sits on the counter, the pearls sink to the bottom. To keep them suspended, you have to aggressively stir the liquid.
The physical principles are exactly the same, just applied to molten rock at 1300 degrees Celsius under immense pressure.
Right.
Chromite is extremely dense. If the magma in the upper mantle were sitting in a quiet, static chamber, the chromite crystals would simply settle to the bottom by gravity and form flat, stratiform layers.
But they didn't form flat layers. They formed floating spheres.
Exactly. To form nodular textures, these chromite aggregates had to be constantly tumbled and kept aloft while they grew concentrically. This requires a dynamic, highly turbulent, rapidly flowing stream of magma pushing its way through channels in the upper mantle.
So it's moving fast.
Very fast. The upward velocity of the magma flow had to precisely counteract the downward pull of gravity on these dense nodules.
It really paints a picture of the Archean mantle not as a slow, creeping mush, but as a violent, rapidly churning engine with literal subterranean rivers of boiling magma.
It does. And the researchers found even more evidence of this extreme environment when they looked at the rocks under a polarizing microscope. They didn't just find pristine magmatic textures. They found evidence of extreme high-temperature plastic deformation.
Okay, plastic deformation means the rock was bending and flowing without snapping, right? Like if I bend a piece of cold steel, it snaps. If I heat it in a forge, it bends.
Exactly. They documented pull-apart textures in the chromite grains, where the solid crystals were literally stretched and fractured while still semi-molten.
Wow.
Even more compelling, they found kink bands within the microscopic olivine crystals trapped inside the chromatite pods.
How does a crystal get a kink in it? I thought a crystal lattice is supposed to be this rigid, repeating geometric structure.
Well, under extreme stress and heat, the atomic planes within the crystal lattice can actually slide past one another without the crystal breaking entirely. This is called a slip system. The specific slip systems that create the kink bands observed in the Dongguanzi olivine require very specific conditions. They only activate at temperatures between 1,000 and 1,200 degrees Celsius.
So the rock is basically functioning as a geological thermometer. It's telling us, I crystallized in a turbulent river of magma, and then I was subjected to massive tectonic shearing forces while I was still unimaginably hot.
And this is the conclusive proof that the stagnant lid theory was wrong. The Dongguanzi ophiolite proves that by 2.5 billion years ago, the Earth had a fully functioning plate tectonic engine.
That's amazing.
The seafloor was spreading, the mantle was convecting rapidly, and oceanic crust was being thrust onto continents. When you look at the Himalayas today, or feel the tremors of the San Andreas Fault, you are witnessing the modern operation of a mechanical engine that was fully up and running in the Iraqi neon.
It's just incredible to think about. We use these microscopic kink bands and nodular textures locked inside an armored chromium pod to prove the movement of entire oceans billions of years before the first animal ever existed.
Geology is wild.
It is. But an ophiolite doesn't just tell us that tectonic plates crash, it can also tell us the precise forensic details of how they crashed. Which actually brings us to our third stop on this journey. We are moving forward in time, from the ancient Cratons of China to a much younger, more complex tectonic scar, the Zagros suture in northern Iraq.
Right. We are fast-forwarding to roughly 30 to 50 million years ago during the Eocene and Oligocene epochs. This is the era when the Arabian plate began its slow, grinding collision with the Eurasian plate.
Which is an ongoing thing, right?
Yes, and this collision is what closed the ancient Neo-Tethys Ocean and pushed up the Zagros Mountains.
So the research we are focusing on here is by Saba Ismail and colleagues, and they're looking at the Walash Noaperdan group in the Colander and Rayat areas of Iraq. They are basically digging through the crushed remnants of the Neo-Tethys ocean floor, and they found something highly unusual. In the exact same geographic region, they found two fundamentally different types of chromitite rock.
Yeah, they discovered bodies of high aluminum chromatites sitting in close proximity to high chromium chromitite. Now, to a casual observer, they both just look like dark mantle rocks.
Sure.
But to a geochemist, finding these two chemical signatures side by side is a glaring anomaly. The aluminum and chromium concentrations are a direct map of the thermal and chemical conditions of the mantle when the magma melted.
Let's break down the chemistry a bit. Why does aluminum versus chromium tell you where a rock was born?
It comes down to how different elements behave when solid mantle rock begins to melt. Aluminum is what we call an incompatible element in the deep mantle. It prefers to partition into the liquid melt relatively easily.
Okay.
Chromium is highly compatible. It wants to stay locked in the solid residual rock.
So to get the aluminum out into the magma, you really only need to melt the mantle a little bit.
Precisely. High aluminum chromatites are associated with what we call a MRB affinity, mid-ocean ridge basalt.
Got it.
This magma forms at relatively shallow depths in the upper mantle, right where two tectonic plates are gently pulling apart, kind of like the mid-Atlantic ridge today. The decrease in pressure causes a low degree of partial melting, roughly 10 to 15% of the mantle rock melts. This shallow, low-degree melt extracts the aluminum, leaving the chromium behind.
Okay, so high aluminum means shallow, pulling apart magma. What about the high chromium rocks?
To get a high chromium magma, you have to melt the mantle much more extensively, driving the melting past the point where the aluminum is already gone, forcing the stubborn chromium into the liquid.
And that takes a lot of energy.
It does. This requires a bonitic magma, which forms at much higher temperatures, at a higher degree of partial melting, sometimes over 20%.
And how do you generate that much heat and melting deeper in the mantle?
You add water. When a dense oceanic plate subducts, when it dives deep into the mantle beneath another plate, the immense pressure squeezes the water out of the subducting rock. That water percolates upward into the overlying wedge of mantle rock. Adding water to the mantle drastically lowers its melting point, causing an intense, fierce melting episode.
Wow, okay.
This deep water flux melting creates the high chromium bonditic magmas, which typically erupt as island volcanic arcs.
So we have a massive geological contradiction here. High aluminum rocks represent shallow plates pulling apart. High chromium rocks represent deep plates smashing together and diving. How on earth do you end up with both of these environments preserved in the exact same mountain range in Iraq?
It requires a highly specific, dynamically evolving tectonic environment known as a back arc suprasubduction zone. It is essentially a tectonic cascade effect.
I need you to build a 3D model of this in my head. A back arc supersubduction zone. What is physically happening to the crust?
Okay, imagine two oceanic plates colliding. Plate A is older, colder, and denser, so it begins to subduct beneath plate B. As plate A dives down, it releases its water, triggering that intense, deep mantle melting we just discussed.
Right.
This magma rises through plate B, forming a chain of volcanoes, an island arc, that forms the high chromium rocks.
Okay, so I have the volcanic arc forming above the diving plate. Where does the shallow melting come in?
Here's the mechanical twist.
Eh,
As plate A dives into the deep mantle, it doesn't just slide smoothly, it sinks steeply, and gravity pulls the hinge of the subducting plate backward. This is called trench rollback.
crunch roll back. Got it.
This backward pulling creates a massive suction effect, dragging the overriding plate B toward the trench.
So the plate that is sitting on top is being stretched toward the collision zone.
Exactly. And the tension becomes so great that plate B literally tears apart behind its own volcanic arc. This tear opens up a new spreading center, a back arc basin. As the crust rips open, fresh shallow mantle upwells to fill the void, undergoing that low-degree decompression melting to form the high aluminum MORB rocks.
So an ophiolite isn't just a piece of ocean floor, it is a forensic snapshot of a tectonic car crash.
It really is.
The diving plate creates the high chromium rocks in the front, and the resulting mechanical tension rips the crust apart in the back, creating the high aluminum rocks. And millions of years later, this entire chaotic system gets swept up and smashed into the continent, preserving both signatures side by side.
It is the ultimate forensic geology. But Ismail's team didn't stop at the major chemical elements. They looked closer, doing a microscopic autopsy of the chromite crystals, and they found tiny inclusions of a completely different mineral trapped inside.
Laurite.
Laurite is ruthenium sulfide, RoS2. Ruthenium is a platinum group element. These are some of the rarest elements on Earth. Finding platinum group minerals is always significant because their behavior in magma is incredibly complex. But what Ismail's team focused on was the specific morphology, the physical shape of these laurite inclusions. They were perfectly euhedral.
Euhedral meaning they had perfect, sharp, completely uneroded geometric crystal faces.
Exactly. If these laurite grains had been rounded, pitted, or jagged, it would indicate that they had crystallized. But then the magma chemistry changed, perhaps becoming more oxidized or sulfur-rich, and the crystals began to dissolve or corrode before the chromite trapped them.
But because they are perfectly sharp, they tell a specific chronological story.
Yes. The euhedral shape proves that the laurite crystallized directly and freely from a highly primitive, high-temperature, sulfur-undersaturated magma. They precipitated early, floating in the melt. Shortly after, the physical conditions shifted just enough for the massive chromite crystals to begin growing. The chromite grew around the laurite, sealing it away perfectly.
Like a fly trapped in amber.
Exactly like a fly in amber. Except the amber is a refractory mantle rock forged 40 million years ago, and the fly is a microscopic crystal of ruthenium.
It is deeply humbling, honestly. The massive landscape-altering forces that push up the Zagros mountains, the fluid dynamics of subducting plates, all of it is governed and recorded by these microscopic atomic rules. And this perfectly transitions us to the next phase of our deep dive. We have looked at the vastness of the early solar system and the grinding of massive tectonic plates. Now, we are going to push the microscope to its absolute limit. We are zooming all the way down to the atomic lattice itself.
We need to understand the structural engineering of these minerals. How does a rock actually survive 2.5 billion years of tectonic crushing? We're looking at a 2004 crystallographic study by Davide Liniaz and his team focusing on the spinel structure.
Now, we have used the word chromite repeatedly today, but chromite is technically just one specific mineral within a much broader, structurally defined family called spinels.
Correct. When a crystallographer talks about a spinel, they aren't necessarily talking about a specific chemical formula. They are talking about a specific architectural framework of atoms. Imagine a microscopic scaffolding. The foundational building block of a spinel is a nearly perfect, face-centered cubic, close-packed array of oxygen atoms.
So you have a three-dimensional grid of massive oxygen atoms tightly packed together.
Yes, but within this tightly packed oxygen scaffolding, there are empty spaces, tiny geometric cavities, and the metal atoms, the magnesium, the iron, the chromium, have to find a place to sit within these cavities. There are two distinct types of seats available in the spinal theater.
Right, the tetrahedral sites and the octahedral sites. Let's describe the geometry of these seats.
A tetrahedral site, which we designate as the T site, is a cavity surrounded by exactly 4 oxygen atoms, arranged like a triangular pyramid. An octahedral site, the M site, is a larger cavity surrounded by 6 oxygen atoms, shaped like 2 pyramids attached at their bases, basically a diamond.
What Linaz and his team wanted to know was what happens to the overall architecture of this scaffolding when you start swapping out the metals sitting in those seats. They created what is called a solid solution series.
They went into the lab and synthetically grew a series of crystals. On one end of the spectrum, they grew pure magnesiochromite. In this crystal, magnesium occupies the tetrahedral sites, and chromium occupies the octahedral sites. Then, step by step, they began substituting iron, specifically the ferrous A2 plus ion, in place of the magnesium. They created a spectrum all the way to pure chromite, where iron completely fills the tetrahedral sites.
They baked these crystals at 1200 degrees Celsius in a highly controlled atmosphere to ensure the iron didn't oxidize. And then they bombarded them with X-ray diffraction to measure the exact microscopic distances between the atoms.
And this experiment revealed the incredible, uncompromising physical properties of the chromium atom. Because chromium, specifically the trivalent Cr3 plus ion, has an overwhelmingly high site preference energy.
Explain site preference energy. Why does chromium care where it sits?
It comes down to quantum mechanics and crystal field theory. The electron orbitals of the Cr3 plus ion interact with the electrical field generated by the surrounding oxygen atoms. When chromium sits in the octahedral M site, surrounded by 6 oxygens, its specific electron configuration achieves a state of massive energetic stabilization.
Oh, wow.
It is the lowest possible energy state for that atom. Because physics always favors the lowest energy state, chromium demands the octahedral site and absolutely refuses to enter the tetrahedral site.
It's the ultimate VIP atom. I mean, it walks into the club, looks at the pyramid-shaped chair and the diamond-shaped booth, immediately claims a diamond booth, and once it sits down, it exerts so much energy to stay there that you cannot force it to move.
That's a hilarious analogy, but it's spot on. And the X-ray diffraction data mathematically proves this stubbornness. Across the entire synthetic series, whether the surrounding crystal was loaded with magnesium or loaded with iron, the exact distance between the chromium atom and its 6 oxygen hosts, the MO bond distance stayed rigidly, aggressively constant at exactly 1.995 angstroms. It did not budge by a fraction of a picometer.
Okay, if the chromium is bolted to the floor at exactly 1.995 angstroms, what happens when you start forcing larger iron atoms into the tetrahedral seats?
That is where the structural tension arises. The magnesium atom is relatively small. When it sits in the tetrahedral site, its optimal bond distance to the oxygen is 1.965 angstroms. It fits comfortably. But the ferrous iron atom is physically larger. It requires a bond distance of 1.998 angstroms to be stable.
If we think of this as a game of microscopic musical chairs, chromium grabs the octahedral seat and refuses to move. Magnesium is sitting comfortably in the tetrahedral seat. But then iron comes along. Iron is bigger. It tries to sit in the tetrahedral seat, but it's too tight. And because chromium won't give up any space, iron has to physically push the oxygen atoms outward, stretching the tetrahedral chairs to fit.
That is exactly the mechanism. The substitution of the larger iron atom forces the entire unit cell, the basic repeating geometric box that holds the crystal together, to physically expand. The TO bonds stretch to accommodate the iron, while the MO bonds stay rigidly fixed.
But this stretching doesn't just change the physical size of the box, right? It distorts the electrical fields inside the crystal.
Yes. To measure this, Linaz used a highly sensitive technique called Nussbauer spectroscopy.
Let's dive into that. How does Nussbauer spectroscopy actually see an electrical field inside a rock?
It relies on gamma rays and the Doppler effect. You take a radioactive source that emits a very specific frequency of gamma rays. You vibrate that source back and forth using the Doppler effect to subtly shift the energy of the gamma rays, similar to how a police siren changes pitch as it drives past you.
Right.
You fire these gamma rays through the crystal. The iron nuclei inside the crystal will only absorb the gamma ray if its energy perfectly matches the nuclear energy levels of the iron.
And the nuclear energy levels of the iron are dictated by the electrical environment around it.
Exactly. If the tetrahedral site is perfectly symmetrical, you get a clean, sharp absorption reading. But because the unit cell is physically stretching to accommodate the iron, while the chromium framework refuses to yield, The electrical field around the tetrahedral site becomes slightly asymmetrical, slightly distorted. This changes the energy needed for the iron nucleus to absorb the gamma ray.
And the machine detects this as a broader, messier signal.
The researchers identify this as short-range order effects. Even if the overall macroscopic crystal looks uniform, at the local atomic level, the specific arrangement of having a larger iron atom sitting next to a smaller magnesium atom creates subtle, localized electrical tensions and distortions in the lattice.
Why does all this microscopic stretching and electrical tension matter to the macro world? Like, why do we care?
Because the macroscopic durability of the Earth's crust is entirely dictated by the microscopic rigidity of these atoms. The absolute refusal of the chromium atom to yield its 1.995 angstrom bond distance creates an incredibly refractory, rigid framework.
Oh, I see where you're going with this.
It is the exact atomic reason why those Podiform chromitites in the North China Craton could survive 2.5 billion years of tectonic crushing, mantle convection, and abduction without being obliterated. The strength of the mountain is born in the immovability of the atom.
Wow. We've gone from the violent collisions of continents down to a single atom stubbornly holding onto a fraction of an angstrom of space. That is wild. For the final part of our deep dive, we are going to look at what happens when this deep earth element finally breaks the surface. We spent this whole time looking at chromium locked in dark, dense, metallic rocks in the mantle or out in the freezing void of space.
Right, because chromite is not a glamorous mineral. It's opaque, black or brownish black, and very dense. It is an industrial rock.
But when chromium manages to escape the deep mantle, travel up to the shallow crust, and interact with an entirely different set of surface elements, it produces a mineral called crocoite. And crocoite is anything but industrial. It changed human history, art, and transportation.
Crocoite is a profound geological anomaly. Chemically, it's a lead chromate, PbCrO4. And physically, it is stunning. Instead of dark metallic chunks, crocoite forms elongated, prismatic, needle-like crystals that are highly translucent and violently colored, vivid hyacinth reds and brilliant fiery oranges.
If you look at a museum specimen, it literally looks like a cluster of glowing, frozen saffron threads shooting out of the rock. In fact, that visual is where it gets its name. It comes from the Greek word krokos, which means saffron.
The recorded history of crocoite begins in 1766 in the Ural Mountains of Siberia. A German mineralogist named Gottlob Lehmann was exploring the Berezovsk gold mine, and he discovered these vivid red crystals. Because chemistry was still in its infancy, they didn't have the tools to fully analyze it. They simply called it Siberian red lead, assuming it was just a strange oxide of lead.
It stayed a chemical mystery for over 30 years. Nobody knew what made it so brilliantly red. Until 1797, when a renowned French chemist named Louis-Nicolas Vauquelin got his hands on some samples.
Vauquelin was a master of analytical chemistry. He took the Siberian red lead and boiled it in hydrochloric acid. This reaction precipitated out the lead as lead chloride, leaving behind a highly colored, unknown liquor. He isolated the oxide from this liquor, placed it in a charcoal crucible, and heated it to immense temperatures in a forge. The carbon stripped the oxygen away, and what was left in the crucible was a network of hard, brittle, steel-gray metallic needles. He had isolated a brand new, previously undiscovered element.
And because the chemical salts he made from this new metal produced such an incredible spectrum of vibrant colors, bright yellows, deep greens, intense reds, he named the element chromium, derived from the Greek word chroma, meaning color.
The irony is profound. As we've seen, 99.9% of the chromium on Earth is locked up in dull black chromite in the mantle. The only reason this element was discovered and named for its vibrant colors is because of the freak geological accident that created the crocoite in Siberia.
Let's talk about the mechanics of that accident. Why is a rock that produces such beautiful colors so incredibly rare?
Because it requires the intersection of two distinct geological environments that almost never meet. You need a source of chromium. As we know, chromium is highly compatible in the mantle. To get it to the surface, you need pieces of the deep mantle, like the ophiolites or serpentinites we discussed earlier, to be thrust all the way up into the upper crust.
Okay, you have a deep earth rock pushed to the surface.
But then you need a source of lead. Lead behaves oppositely. It is highly incompatible in the mantle and tends to concentrate in the shallow, oxidized hydrothermal veins of the upper continental crust, often as the mineral galena.
So you need a geological elevator to bring deep mantle chromium up, and park it exactly next to a shallow crustal lead deposit.
And then you need heavily oxidized groundwater to flow through both rocks simultaneously, dissolving the lead and the chromium,
Yeah.
mixing them together, and precipitating the lead chromate crystals in the cavities of the rock.
Wow, that's specific.
It is. This specific sequence of events is so vanishingly rare that over 95% of the world's finest, large-scale crocoite specimens come from just one tiny location on Earth, the Dundas district in Tasmania, Australia. A specific fault zone there, perfectly juxtaposed a chromium-rich serpentinite body directly against a lead-rich carbonate rock.
But long before the massive deposits in Tasmania were found, the small amounts of Siberian crocoite set off a massive cultural explosion in Europe, because chemists realized that if you took this beautiful red crystal and ground it into a fine powder or synthesized it in a lab, it made an intensely bright, completely opaque, stable yellow pigment.
They called the pigment chrome yellow. In the early 1800s, producing a bright yellow paint was incredibly difficult. Most organic yellow dyes faded rapidly in sunlight. Chrome yellow was revolutionary because it was chemically stable, it held its brilliance.
It became the absolute height of high society fashion. A manufacturer named Andreas Kurtz began producing it in bulk. He used a specific, brilliant shade of Kurtz yellow to paint the carriages of Princess Charlotte, the daughter of King George IV. Suddenly, every aristocrat in Europe had to have chrome yellow wallpaper, chrome yellow textiles, chrome yellow carriages.
But the pursuit of this vibrant color ignored a terrifying reality. We mentioned that crocoite is a lead chromate. Both of those elemental components, when manipulated in this specific oxidation state, are incredibly toxic.
We all know lead is highly poisonous, causing severe neurological damage. But what about the chromium? Chromium in our diet, trivalent chromium, is actually an essential trace nutrient, right? It helps regulate insulin.
Yes, Cr3+ is essential for human metabolism. But the chromium in crocoite and chrome yellow pigment is hexavalent chromium, or Cr6 + Pho. This means it has been stripped of 6 electrons. Hexavalent chromium is a severe oxidizing agent. Because its structure is remarkably similar to the sulfate ion, the human body's cellular transport mechanisms actively pull the Cr6+ into the cells, mistaking it for a necessary nutrient.
Oh, that's horrifying.
It is. Once inside the cell, it strips electrons from the surrounding proteins and DNA, causing massive oxidative stress, double-strand DNA breaks, and mutations. It is a potent, deadly carcinogen.
Handling a solid crystal of crocoite in a museum is generally safe because it's stable. But grinding it into a fine dust in an unventilated 19th century factory, breathing it into your lungs, or mixing it into paint that flakes off onto the floor. It was a deadly occupational hazard. It is a stunning saffron-colored geological masterpiece that functions as a highly toxic cocktail.
And the cultural legacy of that toxic beauty is still visible today. Because that specific shade of chrome yellow, the brilliant opaque color derived from the Siberian red lead that painted the carriages of British royalty, was eventually adopted by the transportation industry for its unparalleled visibility.
You cannot look at a classic American yellow cab navigating the streets of New York City without seeing a direct historical line drawn straight back to Andreas Kurtz, Louis Nicholas Vauquelin, and the discovery of crocoite in the Ural Mountains.
It is a phenomenal trajectory. The element that started out keeping time in the frozen, watery cores of asteroids at the dawn of the solar system ended up marking the taxicabs of the modern metropolis.
Let's summarize the immense amount of ground we have covered today. We started in the chaotic void of the early solar system, watching the radioactive decay of aluminum-26 melt ice inside ancient planetesimals, and we saw how scientists had to build a synthetic phaolite ruler to calibrate their mass spectrometers, ultimately proving that the Earth's water was likely baked into our local neighborhood 2.5 million years after the sun ignited.
We tracked chromium down into the boiling, turbulent Archean mantle of the early Earth, reading the microscopic kink bands and orbicular textures in 2.5 billion-year-old rocks from the North China Craton to prove that the mechanical engine of plate tectonics was fully operational in deep antiquity.
We moved to the Zagros Mountains of Iraq, using the high aluminum and high chromium chemical signatures of ophiolites and the perfect euhedral shapes of microscopic laurite inclusions to forensically reconstruct the violent tearing and subducting of tectonic plates.
We zoomed deep into the rigid, uncompromising atomic scaffolding of a spinel crystal, watching the chromium atom stubbornly refuse to yield its octahedral seat, forcing the surrounding lattice to physically stretch and distort around the intruding iron atoms.
And finally, we followed chromium up to the surface surface, where the freak geological mixing of deep mantle rock and shallow lead veins created crocoite, a mineral that gave us the element's name, painted human history in brilliant yellow, and concealed a deadly carcinogenic toxicity.
It has been a deeply comprehensive deep dive. But before we sign off, I want to leave you with one final provocative thought to mull over. Throughout this entire journey, we have seen how these chromium minerals act as the ultimate recorders of the deep past. They capture the primitive magmas, the ancient waters, the atomic forces of billions of years ago.
Right, they are unparalleled time capsules.
But consider the extreme rarity and precise sensitivity of these formations. The exact geological pressure needed to perfectly preserve a euhedral laurite crystal. The highly specific microscopic distortion in the spinal lattice caused by a shifting electric field. The 1 in a million fall line required to synthesize crocoite. Could the incredibly specific isotopic and structural signatures of these chromium minerals become our literal treasure maps for the future?
How do you mean?
As humanity begins to look outward as we plan to mine asteroids for water to sustain space colonies, or as we develop technology to harvest deep ocean ridges for the rare platinum group metals needed for next-generation energy grids, we will not be using standard geographic maps. We will be looking for these exact microscopic anomalies. The subtle Nussbauer distortion in a chromium spinel, or the precise 53 chromium isotope ratio measured by a mass spectrometer on a piece of space phaolite, might be the exact compass we use to navigate the next age of planetary expansion. The keys to surviving our future in space are quite literally locked in the atomic architecture of our deep past.
When you look at a rock sitting on your desk, you are not looking at a static object. You are looking at a deeply complex, layered history of the universe, waiting for the right instrument to read it. The diagnostic landscape might be muddy, the math might require a synthetic ruler, but if you know how to read the distortions in the lattice, these secrets of the cosmos are sitting right there in the palm of your hand. Thank you so much for joining us on this deep dive. We respect your time and your immense curiosity, and we hope you keep finding the incredible hidden stories in the everyday world around you.